So as you can probably tell, my project is going to be about lasers. Now, we all like to have fun with lasers occasionally, shine them into people's eyes, burning their retinas, blinding them, great stuff like that. But the thing is, most people don't actually know how lasers work. So to start off, laser actually means light amplification by stimulated emission of radiation. And if you notice, I'm using a laser during my lasers description thingy. So some basic info about lasers. They're monochromatic, which means they have a single output wavelength, or they have pure color with an extremely narrow like line width, so like the light doesn't spread out everywhere like a flashlight. Lasers can have all different kinds of wavelengths, from ultraviolet to infrared. Different wavelengths are used for different things. For instance, UV lasers are generally used for cutting metals and plastics, things of that sort. Lasers are highly directional, which means you can point at something and it'll just stay right there. It doesn't spread out like a flashlight, kind of like we already talked about. And all waves of a laser are in like phase with one another, all exactly in phase. So kind of like we talked about in the waves chapter, you can have constructive interference. Well, this is kind of like always having constructive interference. So if you have, if the wave is like that, all the other waves in that laser are going to be matching up peak to peak, trough to trough, like that. Now, to understand lasers, we have to understand some things about atoms. Okay? So, atoms, we'll just use a hydrogen atom because it's easiest. So you got your positively charged nucleus right here. You got first energy level, which was poorly drawn. Should probably be more like that. You got your second energy level, third, and so on. So hydrogen only has one electron on the first level, like that. So this is at ground state, whenever the electrons are at the lowest energy level possible, I guess. So they can, whenever a electron goes, that's an arrow, goes up in an energy level, so from the E0 to E1, for instance, it's now in the excited state. The electrons are now in higher energy level than at its ground state. So now this happens, by the classic Schlurp and Blurp method. You have your electron right here, and a photon will come in from over here, comes into the nucleus like that. This thing then pops down, and you're now at your excited state. So this thing comes in, Schlurp, okay? Then it can go back to ground state when this same photon goes out to here, and this goes back down here, Blurp. Whenever it's in its excited state, it'll stay there for a little bit, and then it'll move back down because it wants to be in its ground state. Another thing can happen though. So you have your electron at its excited state right here. Another photon comes in from here, and whenever this comes through here, both of them pop out like this. And these two photons now are exact copies of each other. So same energy, momentum, wavelength, things like that. And this process right here is called spontaneous emission. Now back to the structure of an actual laser. So what you're going to have is, the first part of it is a little mirror right here, and it's going to have 100% reflectivity, which means pretty much nothing can come out through there. Then the next part is going to be the gain medium. And the gain medium can be made up of solids, liquids, or gases. An example of gas would be carbon dioxide, CO2, or krypton. Liquids are very rare, so there's really not too many of those. Regular solid to be the gain medium. An example of that would be neodymium-doped yttrium aluminum garlet and neodymium-doped yttrium lithium fluoride. So those make up this bit right here, the gain medium. Now the last part of this, the gain medium, what it does, it has all of these atoms in here to create identical photons, kind of how it'll end up happening in the process of spontaneous emission. But the last part of it is going to be another mirror right here, and this is going to have roughly 98% reflectivity. And that's the actual solid piece of it. Now, around the outside, there's going to be some kind of an energy source sort of looping around it, coiling around the gain medium. And this is there in order to raise electrons to a higher energy level or excited state. And this process is called optical pumping. Now let's take a closer look at the inside of the gain medium. So we use, let's say, black for atoms at the ground state and red for excited state. So initially, this is on the inside of the gain medium, got a bunch of atoms and stuff all at their ground state. Now, the energy source is going to emit photons, which make these atoms go to a higher energy level. So they start, what is it? Emit photons, not emote. Emit photons, not emote. Yeah, anyway. So now all these red ones are going to be excited, atoms at the excited state. Now, how we talked about earlier, after a minute, it'll shoot a photon out. So now there's a little photon that just got shot out of this one. This goes back to its ground state. And so the next thing that'll happen, this photon will probably end up interacting with one of these other excited atoms. When this goes into here, as we talked about previously, two identical photons are going to get shot out, which starts a chain reaction making a bunch of photons of the same kind. And only photons with the same amount of energy and momentum would be part of this chain reaction. All the other ones will, so if this is the gain medium right here, they'll fly out here and stuff. So this is why they're really strongly coherent and monochromatic, because it's only identical photons in this chain reaction. Now this is very important. For a laser to work, there has to be more excited atoms in here than atoms at the ground state. So if all these were at the ground state and like this, well, the laser wouldn't work because there's way fewer excited atoms than atoms at the ground state. So now let's take a look again at this mirror right here of 98% reflectivity. So it's 98%, so it'll for the most part bounce the photons back, just like this one of 100% over here will. However, it does allow some of the energy to end up being emitted out of here. So some of these photons are going to be flying through here, going this direction, which is why you can see it, which is why whenever I point this laser, these are all of the photons that ended up escaping the mirror with only 98% reflectivity. So that's how lasers work. Now, some common uses for lasers, as well as blinding people, they can also be used to fix eyes to give people better vision. So it's a good process. Blind them, fix them, all with the same, all with lasers. They can also be used in barcode scanners to measure distances. For instance, what they'll do is shoot really powerful lasers up at the moon and have them bounce back, and since it doesn't disperse like a flashlight, that's how they are able to gauge the distance it was to the moon. It also has a lot of military uses as well. For instance, the Boeing airborne laser, it was created on a Boeing 747, and it can take out or kill, I guess, ballistic missiles of short or medium range when they're in their boost stage. One you may have heard of, though, is the Strategic Defense Initiative, also known as Star Wars. Now, this one is both Earth and space-based lasers that are used to destroy intercontinental ballistic missiles that people are shooting at us being the United States. That's it.